Hello, I'm a senior here at Stevens Institute of Technology, and I'm here to present to you our efforts towards the NASA RMC Robotics Challenge. We have chosen an ambitious project and are in search of sponsorship. This competition stems from NASA's Artemis program. The agency is taking the next step in space exploration by obtaining water from the lunar South Pole. As a team, we are competing to build a robot that can most efficiently excavate the water simulant, called icy regolith. And we will face competitors from universities across the nation. To give a better idea of the competition and its requirements, please take a look at this graphic. The robot, shown in white toward the right side of the arena, will have to travel to a specified mining zone while avoiding any obstacles in its path. Upon reaching its destination, the robot will begin the excavation process. It will dig past a layer of BP1 simulant, a sand-like substance, to reach a hidden icy regolith below. The robot will then transport the collected regolith to the collector bin, where it will be deposited. The competition is to set mass and volume requirements and will reward teams who integrate autonomous control into their system. Lastly, the robot must complete all of these tasks and collect at least 1 kilogram of icy regolith in under 15 minutes. In order to overcome these challenges, the team has identified 3 major mechanical subsystems. A drivetrain operating with 4-wheel tank drive, a conveyor belt-based excavation system exhibiting 2 degrees of freedom, and a deployable dispensing belt which will store and deposit the regolith into the collector bin. The process behind this design will be detailed in the next few slides.
So starting with the chassis, we will traverse the lunar surface with a tank drive system so that we can control each side independently. That way that we can turn in a small diameter, as well as having customized wheels with cleats on them for optimal stability while driving over rocks, craters, and while digging the BP1. Once we enter the mining area, we will deploy our end effector, which is a conveyor belt used to remove material from the ground and deposit into the storage area. Doing so, we will need to move from the starting configuration to the digging configuration using linear actuators to rotate the system. Then once we are rotated in an almost vertical position, we will have a linear translator using a rack and pinion to feed into the ground, slowly extending our reach and our depth into the icy regolith area. Our dispensing system will have a few different functions. The first being to receive that excavated material from the conveyor belt, then using a crank slider mechanism to transition from the receiving to dispensing. Once dispensing, a secondary conveyor belt will spin and deposit the material into the trough for points.
So this here is a systems level electrical diagram for the various components on our rover, ranging from the main computer and the microcontroller to all of the various sensors that we will be using for localization, as well as the motors. Our team opted to use Robot Operating System, ROS, in order to run all of the software for our rover. So we can see in this diagram that we have 3 primary systems in our rover, ranging from the autonomous system, the drive system, and the mission control system.
The software side of the team has been heavily focused on the localization and navigation portion of the total software system. This figure here shows how information will flow through the robot software architecture. On the left, it starts with sensors feeding information to various nodes to help produce an estimated position and map. This will be used by a path planning node to produce a path for the robot to follow. We've actually been able to start prototyping one of our localization systems. On the screen, you can see that we have been able to identify an April tag, a visual beacon, and determine how far the camera is from the plane that the April tag is in, thus giving us the ability to determine the robot's distance from the beacon. The team has also been working on the simulation side of things, where we have been working and testing out various path planning, localization, and mapping packages available openly in ROS for us to use, which we will later translate to our actual robot.
On the screen, you can see a high-level project schedule of the events that we need to hit up until the competition date in late May. To date, the team has secured $25,000 from the Student Government Association here at Stevens and $1,400 from the Stevens Mechanical Engineering Department. Though those funds are significant, they do not cover travel expenses, and we hope to raise an additional $12,000 for travel expenses. We hope to garner additional funding and mentorship from L3Harris to further support prototype construction, development of novel mechanisms, purchase of necessary electrical components, and to compete with a truly marvelous robot at NASA's Kennedy Space Center. Thank you.